That is what we can look up in tables in literature. And when we increasing temperature means solubility increases as well. So arrow up always means increases. Let's look to another example. We have carbon dioxide, CO2, and we know we can produce sparkling water, CO2 plus water forms H2CO3, hydrocarbonic acid. What are you expecting here when we are increasing temperature in this example? Does it increase solubility? It decreases. In this example, temperature increasing means solubility decreasing. Arrow down. If we try to solve a gas in a liquid and we heat it up, the liquid, the gas bubbles are emitted. I think so. Yeah, I think so, yeah. Well, sometimes we have a so-called oversaturated solution. Oversaturated solution. Do you know what that means? Yeah, you have to be a little bit careful in how to describe it. In science, you always have to be exact. And oversaturated solution, you can produce it when you put, let's say, 400 grams of sodium chloride. Normally, only 350 grams can be solved at 20 degrees. But you put in 400 grams. What happens to the rest of the NaCl, which not can be solved in 1 liter at 20 degrees Celsius? It sinks to the bottom. So you have crystals on the bottom of your liter of water, not solved. Now you heat it up. What happens in the phase when you heat it up? The rest of that, which is now at the beginning, it was laying on the bottom, can be solved. Let's say you heat it up to 80 degrees Celsius, and now at 80 degrees Celsius, you can solve 400 grams NaCl in 1 liter of water. At that stage, at 80 degrees, it is again a saturated solution. But not oversaturated. Because at 80 degrees, you can solve 400 grams. But now you cool it down, and in this intermediate phase, when it is cooling, you have partially more solved than in reality you can solve at that temperature. It takes a while, but then it will crystallize again the sodium chloride. And then the particles, but that takes a while. For a moment, you have solved more than normally possible. But when it has time and it's cooling down to 20 degrees, at some time, you again have 358 grams solved, and the rest as particles, as crystal particles on the bottom. But in that intermediate phase, when it's cooling, it could happen that you have more solved than possible because it takes a while until it's crystallizing. And that is what we call an saturated solution. So that normally means, coming back to sodium chloride, in water at 20 degrees, 358 grams can be solved. In 1 liter. So adding more means NaCl crystals on the bottom, which are not solved. When we'd like to have the figure, again, we have our volume, 1 liter. This is our volume, 1 liter, and we have sodium chloride on the bottom, particles, crystals, not solved. So this additional NaCl stays solid on the bottom. So saturated means exactly the maximum which can be solved. Saturated solution means the maximum of amount of the component is solved. Adding more, it cannot be solved. Substance remains solid on the ground. So, well, let's talk about a component AB, which can be solved. And this is a, um, a salt, solid salt, solid material. And it forms A+ ions and B- ions. So the solved ions. Well, in the case of NaCl, it is Na+ plus Cl minus. If we have another salt, AB2, then we have A2 plus 2B minus. Example can be calcium fluoride, for example, or calcium chloride. Let's take calcium chloride. Then we have Ca2 plus 2Cl minus as an example. If we have silver chloride, for example, AgCl, we have silver plus ions plus chloride ions. Now let's come to another term. It's called the solubility product. A big L, and for silver chloride, when we write it, the definition is the solubility product is now the concentration of the silver plus ions times the concentration of the chloride minus ions. That's the solubility product.
Excuse me.
Hello?
Excuse me. Solubility product should be KL. L, I think, would be solubility as such.
We always did it in the past as L.
Okay.
You think it's KL?
Yeah.
I never heard it. Let's use L. So L, solubility product. And maybe you are right, but let's take the L. In general, for the AB components, it is the concentration of A plus times B minus, or for AB2, what do you think is the solubility product for this reaction here, the AB2? Yeah, it is A plus times the B minus square. The solubility product for silver chloride, it's a famous example, and it's yeah, discussed quite often in literature. L at 20 degrees Celsius for silver chloride, it is 10 to the power of minus 10. What might be the unit for the silver chloride example? Again, what? Yeah, or liter square. Mole square over liter square. And this is the concentration of silver plus ions times the concentration of chloride minus ions. Well, because we know the silver chloride is solid and we can solve partially to silver plus and Cl minus ions. This is our arrow. And when we have it at a standard normal, the concentration of a silver plus ions is the same as the concentration of chloride minus ions, because it's 1-to-1. And what is the value? When we have the standard, we say it is 1-to-1. The product is 10 to the power of minus 10. What is the value of one of them? Ten to the power of minus 5 mole over liter. Now, this is an example, as I tried to discuss just before. What is the expensive one or material in the silver chloride? The silver. And now we have to get all the silver out of the silver chloride, or the vice versa way. We want to produce silver chloride out of a solution where silver is in, solved. What can we do? Yes, we add chloride. For example, we have a solution of this, of Ag plus and Cl minus ions. And now we adding Cl minus ions. For example, let's say we have now a concentration of Cl minus is 10 to the power of minus 2 mole over liter. What does it mean then for the concentration of silver in the solution? Very good. Maybe sometimes others are answering. Slow down. So that means automatically the silver plus ion concentration is 10 to the power of minus 8 mole per liter. So we reduced by a factor of 1,000, because before we had 10 to the power of minus 5. Now 10 to the power of minus 8, it's a factor of 1,000. So we reduce the concentration of the silver ions in our solution. Think about, it is wastewater, and you have quite a high concentration of silver going down in the sink. Before you do that, add chloride, reduce the concentration of silver ions in the solution, in the waste. Chloride doesn't play a big role. You can add more, and you will have another option to reduce silver out of the silver ions via oxidizing the ions. Then you will get back elementary silver. Yeah. Again. Where are you here? What's this square? This one. Because we have 1A and 2B. The ratio is 1 to 2. So we need 2B minus ions, but here it must 2 plus. Yeah, it must be 2 plus. Sorry, A 2 plus. 2 plus. You're right, here it must be 2 plus. For what? CO. CL. Can you be quiet? I do not understand the question. What? Because it's a 1 to 2 ratio. We have 2 positive charges here in the A, and here we have just 1 negative charge. To have a component not charged, we need 2B. Example can be calcium chloride. Well, let's have the calcium chloride, which is at AB2. Well, we have 2 plus 2 Cl minus. AgCl is a 1 to 1. Maybe we can discuss it in the break. I don't get the point. Come here, because now it's already time for the break. And maybe we can come back afterwards if it's a general problem. We will meet again 10 minutes to 4.